Okay. Okay, yeah, I've got to, anyway, so let's just starting from the reflection principle, right? So I didn't turn on the recording, but now it's already recording. Okay, so the reflection principle, so let's say we're starting from 0x to ny, right? So then, we want to counting all the passes of random walk. So this is the time for and time 0, right, and position x. This is time n and position y, right? We want to counting all the passes from 0x to ny, but and sometime this pass must visit 0, right? This must visit 0. Okay. So the total number of those kind of paths actually equals to the total number of paths from 0 minus x to ny, right? So, okay, so this is the statement, right? So you're starting from 0x, right? This is a simple random walk, and you end with ny, okay? So then the total number of paths which visit 0 and some point, right? Total and 0 some point is equal to the total number of paths. You just starting from 0 minus x and ends and ny. Okay, so, right. This is a very basic observation. The proof is very easy. So you just write this k, right? This k is the first time visit 0, right? It's kind of stopping time. So this is the stopping time. This is the first time of this path visit 0, and you can just define a correspondence between this path, and to this path, right? So you just you do the reflection, right? This part above, right? You reflect it to the down part, And of course, right? So for paths starting from 0 minus x, right? You can do the reflection as well, right? Because now minus x is negative, right? And here y is positive. You must cross 0, right? So you just do the reflection, and this gives you a one-to-one correspondence. This should be right? So that's a mistake. You can define a one-to-one correspondence between these two classes. So this is called reflection principle. Yeah. So I don't have time to talk about this section. In last semester, I basically, I haven't talked about arcsine law, but I talk about the preparation for the arcsine law. So you can read section 4.9 and write a little bit notes. So this is part of your homework. Yeah. So I will just move. We just move to the Markov chain. Yeah. So no questions? Okay. So I will just move to the Markov chain. Oh, there one question. Can we? Yeah. So Jiayao Zhang asked a question. Can we reflect over another horizontal line, otherwise than 0? Yeah, definitely you're right. So you can reflect. Let's say if x is bigger than 1, there's a x equals 2, right? You can reflect with x equals to 1, right? So that's not a issue, right? Just to do some shift, right? That's it. Okay. Yeah. So let's go to the Markov chain. So so you can. So let me. As I told you earlier, right? So this is the slides. by Scott Sheffield from MIT. In this slides, so this slide 20. So he revealed some knowledge, right? So this you probably already know when you undergraduate probability class. So on finite state Markov chain. So in the textbook of Durant, our textbook is more abstract. Just to give you several examples, then we go on to do the theory part. So here maybe it's more, so you can go through this to review the basic knowledge on finite state Markov chain. Maybe I just go through this briefly. So then I will use my notes. Okay. So if you have questions, you can ask. So what is Markov chain, right? So here, let's say we have n+1 state, right? This is a finite state. So all the random variables x0, x1 to xn are taking values in this state space. And this is a finite state space. It's the easiest setting. For instance, right, if we just treat the simple random work we just mentioned, right, the state space actually is just 1 and -1, right? 1 and -1. So this is just convention to write as non-negative integers. Okay. So this xn, right, can be interpreted as a system state and time n. Okay. So we call this sequence a Markov chain. So if the following property is true, so this is called Markov property. So what does this mean, right? What is Markov property or Markov chain means? So it basically means, right? So the future of your state only depends on your current state, right? So let's say your current state xn, right, is I, right? And you want to do the prediction of your future, right, of your next state. So actually, it does not depend on all these things. It does not depend on the past. So this is called the Markov property, right? So the probability, right, this is the transition probability, only depends on the state I, only depends on state I. So this is called Markov property. So this is kind of like a memoryless property, right? So your history does not influence your future. I mean, it might influence in some way, but so like here, right, your history, right, the data of your history is irrelevant of your future. So only your current state I can be, right, can use to predict your future, right? So it's kind of memoryless property. Yeah. Okay. Yeah. So actually, a lot of physical system Markov process. In this chapter, most time we only talk about Markov chain. In general, right? So we study process called Markov process, right? It's a process, stochastic process with Markov property, right? It's basically just a different version of this property. There are also other assumptions, but this assumption is the most important one, right? It's most, I mean, it's the essential assumption, right? So the transition function, the transition probability, right? Transition probability only depends on the state as n and n+1, right? It's a Pij. Okay. So for here, right? So it's a finite state Markov chain. So the transition probability, so here Pij is called transition probability. So Pij, right, for all ij in the finite state space, give you a matrix, Okay. So here we have an example. It's a basic example of Markov chain. So for instance, we consider a very simple, a very baby model of weather, so which has two states. So it can be rainy or sunny. Okay, I think this is a very basic model. You probably already know this in undergrad probability class. So let's say if you are and raining, right? If today is raining, so there's a half chance it will be raining tomorrow, and half chance it will be raining, sunny tomorrow. Right? So if it's sunny one day, right, today, so then there's 0.8 chance, right? It's 80% chance it will be sunny tomorrow, and 0.2 chance it will be rainy, like tomorrow, right? So maybe I just write this. It is a basic example, right? For they only have two states, and stop here. So let this just okay. So let me show you here, but here I cannot really yeah. Okay. So now, so for instance, we consider this model, right? It's okay. Okay. So so here, right, we have two states, right? So this is raining, and this is sunny. So if today is raining, right? So then it have 0.5 chance it will be raining, and 0.5 chance it will be sunny tomorrow, right? If it's sunny, so then there's a 0.8 chance it will be sunny the next day, and 0.2 chance it will be raining the next day, right? So for instance, right, let's say if originally we're starting from initial measure, right, which is given by, let's say P1, P2. So P1 is the probability, so let's say this is state I1, right, this is state 2, right? So P1 is the initial, so P1, P2 gives the initial distribution of either sunny or rainy, right? Initial distribution. And so then what is the transition probability, right? So the transition probability, let's say this is a matrix. So in the first, so here should be, right, if it's raining, so it still be raining. And here it is sunny, then it will be raining. So here is 5. Let me see. Yeah. So this is the transition probability matrix. So here is the transition probability. matrix. Right, so here, this is P1, 1. So from renin to renin, right? So here is P1, 2, from renin to sunning, right? So here is P2, 1, right? From sunning to renin, right? And here is P 2, 2, right? From sunning to sunning, right? So this is a basic example, right? And so I guess in undergraduate probability class, you can compute, right? Starting from mu, right? Give you a transition probability matrix, right? You can compute like mu1. Mu1 is given by mu times p, right? So mu1 is the distribution after you do one iteration, right? So the mu n, right, is given by mu pn, right? So this is just a power of matrix, right? And you can, in some cases, given some conditions, you can compute, right? You can ask a question. So what is the limit distribution, right? In certain cases, right? Under what condition? Right. So this is just one example, right? One example of the finite Markov chain. So actually, this is very important topic. So when you use like Google to search something, the Markov chain model is a basic model used to like the Google, right? The search algorithm. Okay. So there are a lot of discussion in Scott uh, Sheffield's slides. So maybe I using the slides is better because in Notability I cannot do the slides style. Okay. So right, so here right is a representation of a Markov chain using a matrix, right? So here Pij is the Ig entry, right? Ij from those state, right? So the P00, P01, P0M. So this the first row actually gives you, right, starting from 0, right? So you can go to 0, 1, or 2M, right? So if you sum up P0, right, the first row or any row, you should get 0. You should get 1, right? So each row, right? Each row actually is a distribution, right? So all those entries are positive or 0. You sum up each row, you get 1, right? You get 1, right? So this is this condition, right, for each I. So each rows, right? So each row sum to 1. And this is a matrix has a name. This is called stochastic matrix. It's called stochastic matrix. And this, because this is stochastic matrix, right? Automatically it has, so I should write on the iPad again, but if you know, so I can be a little bit fast, right? So actually this matrix A, this stochastic matrix A automatically have like 1, 1, 1, 1, 1, right, as a right eigenvector. Right, this is a priori known because this, right? So if you just multiply A by a column vector, right, unit, not unit, right, is a constant, is a column vector 1, 1, 1, 1, 1, right? So you multiply them, you will get 1, 1, 1, 1, 1, right? So 1 is an aging value, and 1, 1, 1, 1, 1, right? So is the aging vector. Okay. Okay. Yeah. so you can easily check that, right? So just by this condition, right? So if you're not clear, let me know, right? So otherwise I will go. Right, so you can see, right? So Pi is the probability that system in the state I and time 0, and we can do the matrix multiplication, right? So if this is the initial distribution of the state, right, 0 to n, and we do the multiplication. So what's the product, right? If you do the multiplication of row vector of this transition matrix, so we actually get the probability distribution and time 1. So this is just what I mentioned a little bit earlier using the baby model, right? So if we do n product, right? Let's call this A, right? If we do the n product, so we get the probability distribution and time n, right? So yeah, so we can compute the distribution just via matrix vector multiplication. Okay. Yeah. So this is the state. So let's say if we go from state I to state J over n steps, this is Pij. So we probably will go back to this later when we talk about like stationary mirror or anything like that. But so this is just a final state, right? You should be able to know this. Yeah, you can check this. So if we go from state I to state J over n steps, right? So this is representation. So Pijn actually is nothing but just the entry of the product. So A, we call this matrix A is a one-step transition matrix. Then A to n's power, right? Just multiply this matrix for n times. So you get the transition matrix. So then A to power n is the n-step transition matrix. So there are also a lot of other discussions, but I will just let you to read that. So we will go back to this when we talk about ergodicity and stationary mirror asymptotic behavior. So so you probably already know this. So when you study undergraduate Markov chain, so I will just skip these slides, and you can use this to do a review of the Markov chain with finite state. So yeah. Okay. So let's see. So let's okay. Okay, so let's just basically follow the order in the textbook. Okay. So now, so we consider a more general setting and give you several more examples. Okay, so if you have questions, just let me know. So as I said, right, so let's consider, right, we study the state space, right? This is the state space S, and let's assume this is countable, right? It's countable. So in this case, right, for instance, this S can be Z or Z to power D, right? The dimensional, the lattice, or just integers. So as I said before, right? So the Markov chain property, Markov property is just the following, right? If you're starting, right, this is zero times state I0, right? The state I minus 1, right? This is state I. So the transition probability is only depends on I and J, right? Your state and I and J, right? So on the side, it's kind of a memoryless property. So given your current state I, so the rest of the past, right? So this is your past or your history, is irrelevant for predicting the future, right? So this is future J. So we call this we call this the transition probability. Because this transition probability in this very easy setting, right? It's from I to J, right? It's a Pij, right? And you see right earlier, right? So for finite or countable state Markov chain, so you can using a matrix representation. Right? You can using a matrix representation. Okay, so another thing. So I didn't write it here. So this P, right? If you write it like this, so this transition probability does not depend on time. So then this Markov chain actually is a time homogeneous Markov chain, right? In general, right? So this P, right? This P might depend on the time n, right? That might depend on time n. Okay. So, but for simplicity, right? Maybe most time in this, if we didn't specify, so we just think the transition probability does not depend on time. So it's called homogeneous Markov chain, time homogeneous Markov chain. Okay. Yeah. Okay. Okay. So as you see, right? So the basic example, right? Instead of the finite state Markov chain. So here is a random walk. Random walk is the setting, right, of Markov chain. But right, so here, so for each increment, right, because I is fine is ZD, right? It's in ZD. So it's in the lattice, right, in D dimension. So let's because I is IID with a distribution or law mu. So xn is a random walk, right? So from x0 plus this, right? X0 is a constant. It's starting from 0, and each step is IID. Right? Each step you move according to kasi I, which are IID. Okay. So xn is a Markov chain. It's a Markov chain. So why this is a Markov chain? So you can easily check the condition, the Markov property, this condition directly. Why, right? So why, right? Because right when you compute the whole thing here, right? So given I, you already given I, right? So xn plus 1 equals to j can be write directly like this, right? So this p xn plus 1 equals j condition to xn equals to I can be write directly like this, right? And it really does not depend. I mean, even you put a few more terms here, right? The past, it doesn't change anything, right? It doesn't change anything. And why it doesn't change anything? Because this increment, right? This increment only depends on j and I, right? And this random variable actually is independent of all xn, right? All the previous things, right? So here we just get a constant, right? A constant. So Pij, right? Pij is it just it only depends on the distribution of increment cos I n plus 1, right? So this is a Markov chain. Right? You can check the property very easily. Okay. Yeah, probably a little bit fast, but if you have questions, let me know. And since we already recording, right? So you can play, you can see the video later. Yeah, so I will just move on. So another example is the branching process, right? Is a branching process. So this is just a basic review, right, of how we define the branching process. This is a specific branching process called Galton-Watson process, right? So we talked about this earlier. Right? So this is an example when we talk about martingale's applications or martingale convergence theory. Right? So since this is it's a population model, right? So all the integers, right? So all the state is positive integer, right? Is how many individuals do we have, right, in each generation. So the definition of this population model, right, Zn, right, the branching process is defined as this, right? Oh, sorry, I have a typo here. So here Z0 should be 1, right? So otherwise it's banned. So let me maybe point it here is a little bit better. Okay, so here is wrong. It's 1. Here is 1. Okay. Maybe I just use this. It's better, right? Maybe I just use slides. Maybe I just using the iPad. Okay, so but maybe not that. Okay, so here is 1. Okay. So the definition, right? The definition of yeah, I need still go back. So the definition. So yeah, this is a typo, right? I go to another file. So it's like this, right? So if Zn, right, and nth generation, you have Zn number of individuals, right? So then for each individual, right, they give birth to IID numbers of offspring, right? So this is Kasai I2. So we use this to denote the generation, right? So those Kasai I to some n, right, is IID, Okay, so like each of the I individuals and nth generation, so gives birth to an IID number of offspring, right? So this is called Galton-Watson model. So what is the transition, right? So actually this Zn, right? Zn actually is a Markov chain. Why? Because we can compute that, right? Compute that. So Pij, right, is from the n state, right, and nth generation, they have I individuals, and n+1 generation, you have j individuals. So how to compute that, right? So I didn't write the past, the past, but it really doesn't matter, right? Because as long as you know the nth generation, right, the past history actually does not matter. So we can compute this directly, right? So how to compute that, right? So given Zn equals to I, right? Given Zn equals to I, we can just compute, the probability Zn+1 equals J according to the definition, right? So this is our formula. So okay, so why we can just write like this, right? So because all this Kasai, right, given this ZNI, right, so this is independent. So for n+1 generation, so Kasai M is all independent past. So we just compute, this is conditional probability, right, is just the probability itself. So yeah, so that's it. So it's another example of Markov chain. Okay, so here it says, right, you can see more examples of finite state Markov chains in the slides by Scott Sheffield. So there's another example called the Ehrenfest chain. So it's a very good model, right? It's a very good model. To explain, right, how the thermodynamics. So let me explain this this model a little bit, right? So let's say we have like this is two chambers, right? Two chamber is a box, right? It's divided into two halves, right? It's in two halves, and there's a small door here, right? So we assume there are k particles, right, in the left left chamber, and there are r minus k particles in the right. Right. So those particles are indistinguishable, right? They are just like small ball, right? Hard ball, very small, right? It's like atom. Right? You can think these are air molecule, like oxygen or something else, right? So these are just you can think those are like indistinguishable balls, right? Balls of molecules. Okay, so what's the transition property? Let's just focus on the left one, left half. So we want to study, right, the final state of this the particle distribution in those two chambers, right? So if we have one particle from the right, from 2 to 1, right? So what's the probability? Is what the probability, right? One particle move from 2 to 1, right? So it's like we randomly pick one particle from 2, right? So this is the probability, right? We randomly choose a particle from 2, right? So this is another case, another situation, right? The particle from 2, right, from 1, right, moves to 2, right? From the left, move from left to right. But what's the probability, right? The probability is like k over r, right? So this is the only case, right? It's the only possible scenario, right? So and for other transition, right, it's just 0. Okay, and we can, right, this is the step 1, right? Step 1, right? We can keep doing this, right? So if one particle move to here, right, then the probability change, right? The probability change. Right? So this is kind of, right, let's say, right, so this model actually has physical meaning, right? It makes sense, right? So why, right? Let's say the temperature, right? These two chambers have the same temperature. So the so how to explain this? So they have the same temperature. So the probability, I don't know, right? So how to say that, right? So why? So under what condition, right? This is a physical model, right? And so maybe this is not a physical model, right? Because let's say there's only one particle in 2. There are many particles in 1, right? So definitely there are, so in the end, right, we should expect those two identical chambers have almost the same number of particles. So yeah, but why this makes sense, right? Yeah, let's just think this is a mathematical model, right? So I cannot explain well like why this is a physical assumption, right? Why, let's say the particle from 2 to 1, right, depends on the numbers there. Let's say, right, so it looks like the flow, right, depends on the proportion of particles, right, in each chamber, right, in each chamber. Yeah, anyway, so yeah, so Wang says, right, then because of pressure, let me see. Yeah. You are right, right? Let's say if okay, so I already forgot the basic law in thermodynamics. So it says, right, so now so that's like many years ago. So you probably are right, right? there's a law. So the number of particles like n times p times v equals to RT, which is a constant. Yeah, I forgot this law. But the truth, it should be true, right? If you have more particles, the pressure should be bigger, and they have the linear dependence. Yeah, you are probably right. Yeah. So anyway, okay, let's just focus on this mathematical model, right? So Ehrenfest used this to study, right, like how the particles, how the air molecules move between like two chambers, right, two chambers. You can predict actually as you do this, right, step one, step two, right, time one, time two, and you keep doing this. Maybe in the end, right, in the end, we expect these two, the numbers in two chambers, right, should more or less be the same, right? I mean, it cannot be exactly the same, but it should be close to some equilibrium, right? In the equilibrium, it should be, the particle number should be more or less the same, right? So if you have huge number of particles, right? Let's say this is 10 to 23, right? 10 to 23 or something, right? So then, I mean, it might be fluctuation, but the equilibrium should be more or less the same, right? Okay. Yeah. So you can, there are tons of more examples in the textbook. So you can read that. You can read that, and this is, yeah, you can read that. Okay. So now, so in section 5.1, there are a lot of examples. I will give maybe possible one, like in homework, let you to check, do some computation. But we don't have time, right? You just skip all other examples. Let's talk about the mathematical side or abstract side of Markov chain. So actually, this is probably not a very easy part. You probably find this very hard. So you definitely need to spend some time to go through all the details in this section and also other section later, right? It's not that easy, but you need to spend time to make sure you are comfortable with all the discussion. So actually the ideas are very easy. Right, so the Markov property, right, is very easy, right? It's, as I told you, it's kind of memory this property. But how to prove theories, right, using this, or how to make this rigorous mathematically, is in this section, right? I guess I have like 30 minutes. Okay, let me go through this. If you have questions, let me know. But we don't have time to go through all, right? So I've just pointed the difficult part, right? And you need to definitely spend time to read that. Okay, so let's start. So we have, we are working on some measurable space. So this S is a state space. And this is a Breuer, some sigma field on the set S. So it's called a memorable space. And we have a transition probability on this space, right? So P is P. This function has two arguments. It's not really a function, but it has two arguments. So X A, right? So if we fix the first variable X, right, then the second variable is actually a set. It's a set. I shouldn't. I guess this is a typo as well. So this is not S. It's this, right? So this is not S. It's the sigma field on S. This is a Mescal S. So if we fix, right, if we fix X, right, if we fix X, then from A to this is a number, real number, actually is between 0 and 1. So this is a probability mirror on S, on the measurable space. Okay, and if you fix the second variable A, you fix the second variable A, So then this is just a measurable function. Right? If you fix A, right, this is a measurable function. Okay. So this is nothing, right? So this is nothing. Actually, this is just a generalization of the probability matrix, right? The transition matrix I showed you earlier, right? So this is a generalization of the probability density, probability transition matrix I showed you earlier, right? But now we consider more general space, right? So it's not a matrix anymore, right? You can think it's a matrix in infinite dimension, for instance, right? Okay. So what is Markov chain now, right? So we define a Markov chain on this measurable space, right? And the filtration Fn, right, is just generating by x0, x1 to xn, right? So this is the knowledge we know up to time n. So with transition probability p. So what does this mean? What does this mean, right? So given, right, so this is a projection, right? This is a conditional probability. So this is conditional probability, and this is a random variable, right? It's a random variable. And the conditional probability, right, is just the transition. That's the transition probability. Right? So this is xn, right? Xn is a random variable, right? It's a state and n time. So as we said, right, fix b, right, fix b, right? So here b is fixed. This is a yeah, fix b, right? So fix b, right? This is a measurable function, right? This is a function. So these are also a random variable, right? This is also a random variable because xn is changed, right? So this is the definition of Markov chain, right? It's just a generalization of what I showed you earlier, right? It's a generalization of this, of Markov property here. Okay. Right. So this is a history, right? The history, Fn, right? So in general setting, right, we write this as Fn, right? And right, so Markov property says, right, so Fn is not important, right? The important is Xn, right? It's the state at n time. Okay. Yeah. So this is a general abstract definition of Markov chain. Markov chain. Okay. Yeah. Okay. So if we already have this transition probability, and we know the initial distribution, right? This is the initial distribution on this measurable space. So we can compute the probability of a sequence, the probability of x1 to xn, right, which are in some set, right, some events. So how to compute that, right? So this is very easy, right? So this first step, right, is from, so it's x0, right? X0, right, initial state, and b0, right? So this is the first step, right? So then you compute x1, right? X1 is in b1, right? So given x0 in b0, right? Starting from x0, right? So this is the transition probability, right? So transition from x0 to x1, right? But x1 is integrated on all the set b1, right? So you can keep doing this, right? So this is iterative. This is iterative integral, right? It's an iterative integral, right? Yeah. So this gives you, right? This gives you a set of probability measures, right? So this is a set of probability measures on the first n+1 coordinate, right? So, and this set of probability measures is consistent, right? So what do I mean by consistent, right? Is this, right? If you put one more term, which is sorry, this is a typo. It should be in. It should be inside S. So if we put xn+1 in S, right, this is a whole set, right? It agree with each other, right? It agree with each other. Why it agree with each other, right? You can just put one more terms here, right? One more term here. you integrate on S, right? Then this is a probability xn, right? Integrated with dxn plus 1. But here is S, right? The whole set, right? As we know before, right? Given fixed x, right? So this is a probability measure, right? So this is the probability measure, right? So if this A is a whole set, right? So the integral is 1, right? So this gives you the consistency. Okay. So what does this mean, right? So this means, right, starting from initial state, right, we can compute the probability. We can compute the probability. A sequence, we can compute a sequence of probability measures, right, on the first n terms, of the Markov. Now we didn't check its Markov chain, but the first n term of the stochastic process. Okay. So then with the abstract theory, right, Kolmogorov extension theory, so which requires this measurable space is nice, but this nice is a very general condition, right? I mean, in general, right, any Polish matrix space should be good enough. So you don't need to really worry about how nice it is, right? Almost all the space you can construct, I mean, usually you work with, right? It's nice. So we can use Kolmogorov extension theory. So this is a mirror, right? It's a mirror on the first n+1 coordinate, right? And also these sequence of mirrors are consistent. So we can use that to construct a mirror, right? We call this mirror depends on the initial state P mu. So this is the probability mirror on infinite sequence space, right? So this is, we call this sequence space is S, but to the power of natural numbers, right? From 0 to infinite, right? So this is also the sigma field is also generating by the sigma field S. Okay. So this P mu, right? If you just restrict the P mu to the coordinate, to the first few coordinate, then we just get the previous distribution, right? It's the extension theory. So if we project P mu to the finite dimension, we just get this mirror. Okay, so this is a Kolmogorov extension theory. Okay. Okay, so this is like a decomposition theory, right? It's kind of, it's just a remark, right? Let's say this mu is an initial measure, right? Initial measure. And the initial measure, right? So give charge to x, right? Different x. Right? X is in S, right? In S. And so for different x, we can also define so this is Dirac and x, right? Starting from x, we can define the measure according to the Kolmogorov extension theory as well. So actually, this P mu A is just the integral of this. As long as you know, right, from every point x, right, you know the Markov chain, right, the trajectory of the Markov chain. So you integrate with all this mu, right, you get everything, right? So this makes sense, right? Yeah. Okay. Okay. So all the following discussion, right? Because sometimes later we need to define some stopping time. We want to prove some theory regarding stopping time and do the shift. So this is one of the advantages of using the sequence space, right? So all the measure, right? P mu is defined on the sequence space, and we can define the shift operator very easily, right? So this P mu, right? For instance, later this P mu is defined on the sequence space, and sometimes we need to do the shift, right? So for instance, if you want to consider how many times revisit 0, right? So you want to distinguish the first time, second time, and etc., right? You need to do the shift as we did in the very beginning of this semester, right? So this is the definition of the shift. So, but now we usually starting from time 0, right? So it's the omega, right? The sample temporal point is omega 0, omega 1, right? It's a sequence. And we can define the shift operator, right? We define shift operator, right? We shift to the right for n steps, right? So the original one is omega 0, and now it's omega n. Now it's omega n. We just shift to the left, right? So it's a shift operator, and this is actually very useful. So shift really, what shift really do, you can see more clearly later when you talk about, for instance, the it's called let me called this called the Chapman Kolmogorov equation, right? So why we do need to do the shift, right? So when we do, right, for instance, when you move from x to the point z, right, in m plus n step, right? So it is equals to, right, some decomposition and m step, right? So here the natural treatment, right, is to using like a shift. Yeah. You have questions, or maybe I'm too fast? Okay. So anyway, so yeah, so we can really check, we can really check the measure, right? The measure given by Kolmogorov extension theory, that's called P mu, right? So given this space, right, xn is just the coordinate we defined earlier, and by all the previous construction really gives you the Markov chain. So then is right. So if you condition to Fn, right, you just get this. Okay. Yeah, I didn't prove it here, right? Basically, you need to check. You need to check the details, but I will skip the proof. So it's actually a state, right? So if you, let's say, if you have this property, right? If you have this property, right? So you can define, so this is really a Markov chain. It's kind of, it's a little bit weird. So I think we should say in this way. So how to say this, right? I mean, this is just the definition, right? This is just definition. And this doesn't depend on anything, right? It just give you a probability density distribution and initial distribution mu, right? This is a transition probability function p, right? It's a transition probability p, and this initial distribution mu, right? It doesn't do anything. And given this probability transition probability, given this transition probability p and this mu, right? I mean, this is a priori we can get, and by Kolmogorov extension theory, we can have this p, right? So this p is defined on the whole space, on the sequence space, right? This is p mu. And the construction, right, really gives you the Markov property, give you the Markov chain, right? Okay. So yeah, that's all actually. That's all. Yeah. You see, right? Yeah. So yeah, just to go back to check the details of the proof of this theory, right? And now we will skip that. Okay. So this property, this is the property used definition of Markov chain. You can see, right? So this definition is kind of equivalent to star this equation. Why, right? Why these are equivalent, right? So if you just choose f, as the indicator function of b, right? These are equal, right? These two are equal. right? So to get this formula, well, we need to do like standard theory what we did when we treat the integrals, right? Um, okay, so what I want to say is that this and this are basically the same, right? So compare these two, right? This is just the integral form, right? But this is a matrix. Uh, the probability form, right? This is a conditional probability, right? This is also a random variable, right? But to rigorously prove this, we need a lemma. So in the textbook, it's called class theory. So we want to enlarge the class of F, right? Satisfy this formula. This is a very general F now, but from this formula, F is just the indicator function of V, right? Indicator function of V. I won't talk about this, right? It's basically, right, the monotone class theory is basically the application of Dickin's pi lambda theory. So you can check this, right? So for instance, right, if so how to say that, right? So first we have a pi system A, which contains a whole set, and H is a family of real value function such that these are true, or these two are true. So for any indicator function, right, in this set A, right, the indicator function is in the collection H, and it also satisfies some monotone property and some basic it's additive, and it's also closed for scalar multiplication, something like that, right? This, if you have those properties, right? So we can enlarge these indicator functions to general L infinity functions. Right? So this is just an enlargement, right? It's a monotone class theory. So what I want to say, right, is that this the Markov property, right? So this is also Markov property, right? Let's call this Markov property 1, right? This is a Markov property type 2, right? So these two are equivalent actually. Okay. So you can prove by Dickin's, right, pi lambda theory. So we use that before. Okay. So from this theory, from this formula star, we can do an induction and get a general form. So how to do that, right? So in general, right, we have a multiplication, right? So we can write it out. We can write it out. So this is just right. We project to Fn minus 1, and the expectation is the same. So we can put the Fn minus 1 out, right? I kind of maybe fast, but let me know if you have questions. Okay. Okay. So in general we have we can extend the previous characterization of Markov property to this M product. So to this M product. Okay. Okay. So the third characterization, right? The third characterization. The proof is easier, and by induction basically, and also using basic properties by a conditional expectation, right? So this is Fn minus 1 variable, so we can put it out. We can take it out, right? And now for this part, we can use the previous Markov property, right, in the integral form, right? So we can write this as an integral. We can write this as integral, and we can keep doing this, right? We can keep doing this, right? We can using this trick. We can using this trick again. Using this trick again. So in the end, we get right, the conditional, the expectation of the multiplication can be written as this way. Can be written as this way. This is an iterative integral. It's an iterative integral. It looks very familiar. It looks very familiar to this, right? Looks very familiar to this. But instead of the indicator function, right? So here, when you write this as a expectation, this is just an expectation of some indicator function, right? But instead of the expectation function, right, the indicator function, right, on those sets, right, now it's more general. Now it's more general. It's on the it's integral, right, for functions f0, right, f1 to fn, right? So it's a generalization of previous things. Okay, yeah. So we just list, this is a Markov property, right, used in the definition, right? So only depends on the current state. Right? So if you condition to fn, right, it only depends on xn. It only depends on xn, right? So it's a Markov property. And also, right, this is the first form we use in the definition, right? This is the second form, right, which is the integral form. They are equivalent, right? Oh, those are Markov property. And we want to do more, right? We want to do more. We want to change, right? This is an indicator function, right? This is an indicator function. We want to change this indicator function to some general function, which depends on the future, right? Maybe also depends on xn plus 1, xn plus 2, etc. Right? So we want to change this a little bit. And also, right, we want to introduce stopping time, right? We want to introduce stopping time, not just a fixed things, right? So this gives you, right, when you do all this, right, you introduce the stopping time, right? So you get this. This is a very useful property, right? Usually we call this property Markov property, but all those, right, as I said, right? So we can call this, or the following one, this also called Markov property. But this Markov property with a stopping time capital N usually is called strong Markov property. But we will go back to this later. Okay. So let's just say a little bit more about this property, right? So first we have a random variable. This is a bounded and this is a bounded random variable, right, on the host base, right? So this is y. So the argument actually is a sequence. It's omega 0, omega 1, omega 2, right? This is the sequence on omega 0, right? This is a whole space. Okay, so this mu, right? This mu because, right, when we write a mu here, we mean all, this is conditional expectation, right? So this conditional expectation is taken with respect to the probability measure P mu on the sequence space, okay? So this is a random variable, right? It's not just a number, right? It's a random variable. And what does this mean, right? So first, this is a function. Right? You're starting from x, right? Starting number, and you want to take the expectation of some random variable, right? So this is gives you a function. And what does this mean, right? This means the function phi x evaluated and xm, right? So xm is a random variable. Right? It's a random variable is omega m, right? State and m state. And you're starting from this state and you compute the value, right? So you're starting from this state, right? You compute the expectation. Yeah. So what does this really tell us, right? What does this really tell us? I mean, if your first time saw, it's your first time to see this formula, you might you might know nothing, right? So just a formula, right? But this formula is it's a very good formula, right? So what does this mean, right? So xm, right, is just a number, right? So it's just you're starting from this number. Okay. So now, right, let's so xm is really a random variable, right? It's a random variable, the state and m time. But if you just think this a number, right? Let's fix this state, right? So then what does it mean, right? It's just starting from x, right? Some x, right? You compute the function ey, right? Ey. right, so it's very easy to compute sometimes, right? So, and what does this mean, right? Okay, so this means y, right? Y is a function, right? C time is a shift. So originally you have omega 0, omega 1 to omega m, right? So then you shift m steps to the left, and you kind of get omega m plus 1, etc. Right? So this means, right? This means if you condition against Fm, right? So the later part does not depend on Xm, right? It does not depend on the past, right? So if I just like this, you probably not very easy to understand, right? So we must give concrete examples, right? I won't prove this as well, but yeah, sorry. Okay, yeah, let me see. But Xm depends on the initial distribution. Jia Yao Zhang asked me a question. I think all of you can see the Xm depends on the initial distribution. Yeah, you're right. Yeah, you are right. So Xm, right, but you can see, right? You can see, right? So why? So that's why I don't want to explain more. See this theory, right? You must see some applications. I have several minutes, but let me just, let's say, a few more words and go to the next corollary. You probably better because concrete example, right? So the Markov property basically says, right, if you conditional on Fm, right, conditional on Fm. So if you conditional, you will compute something, right? It basically you just starting from Xm. So you cut all the history, right? It doesn't depend on history. It's something you just starting from Xm, right? So it basically tells you this, right? Let me just give you a concrete example, right? Which is a verse. It's called the Chapman-Kolmogorov equation. So it's just the corollary. So yeah, so it's this. So let's say, right, so you're starting from X, right? This X is the initial state, right? And we want to compute the probability of the random work, right? Of the not necessarily random work, the Markov chain ends and Z, right? From X ends and Z. So what does this mean, right? So when we compute this probability, right, starting from X and stop and Z in m plus 1 step. So then we can just compute so you're starting from X, and you ends and Y in M step, right? Then you're starting from Y, okay? And you stop and Z in N step, right? So then you just sum up with all possibilities and step M. So then that's it. So this is actually indeed the Markov property. This is all the Markov property you should know. Yeah. So which basically means, so if you how to say that? So this basically means, right? So this path has nothing to do with this path. Right? So this part, right, starting from, let's say you're already starting from Y, right? So this path and this part are independent. It basically tells you this, right? Okay. So, right, so in words, right, in order to go from S to Z, right, in M plus 1 step, have to be and some Y and step M, and some Markov property is implied that for a given Y, right, the two paths of journey are independent. So, right, intuitively, this is very easy, right? But if you just look at this formula, right, that's not as transparent as you see. So I think my time is almost there, but maybe we spend more time next time. Yes, this is a video, right? Maybe I can talk a little bit more, right? So this is a very short proof right here. This is all, right? This is all. I just use the previous theory, right? So, okay, so let's say we want to compute the probability starting from X and N and Z, right? I mean, this is a probability, right? The probability actually is right, the expectation, right? Is an expectation. So yeah, we write this as a conditional probability, and we project to FM, then we take expectation, right? Then it's same, right? Of course, right? This is just the property of conditional expectation. So then we write as the expectation form instead of the conditional probability form. We write like this, right? And this term, right, is just the some shift, just some shift, right? So then this is y, right? This is our y, right? This is the shift, right? Make conditional on FM, right? So now, right, now this conditional expectation, right? This conditional expectation, then we can use the theory, right? Then we can use the theory, right? So this is a conditional expectation, right? Which is just given by EXM, y, right? So that's what we use, right? So this whole part, using the Markov property, right? So now we write as we starting from XM, right? And this shift, we delete this, right? So this is our Y, right? Right. So we can write one more step, right? This is expectation. XM is just, you can treat this as a constant. It's a random variable, but you can treat this as constant, right? So we write as P, the probability XM, Xn equals to Z, right? So this is expectation, this is probability, right? So now what do we do? What do we do? We just sum up all possibilities of XM, right? So let's assume XM equals to Y, right? So this is the next step, right? So then we're starting from X, XM equals to Y, right? This is our proof. Right? I will stop here, right? But it's really, I mean, if you first time see this, it might be really confusing, right? But you really need to go through the detail and do several problems. Since I already give you a lot of problems, 5 problems already, maybe I just add 1 or 2. But next week we spend all the time on Markov chain. I want to stop. I want to finish Markov chain for next week, and you need to do several problems on Markov chains. Maybe 6 problems for next week, and this week will be 2 more problems. I really think, right, if you first time see this, you might get confused, but you need to spend some time on that. Okay. So any questions? You can leave, right, if you want, but if you have questions, I can answer now. Yeah, you can unmute yourself, just to say that. No questions?
Can you go back to the reflection?
Yeah, go ahead. Go ahead. No questions? Okay, if no questions, I will just end the.
Sorry, can you explain the last line of the proof?
Okay.
Just the last line should be just the last
this
line.
line.
Yeah.
Okay. Okay. So you see, right? So so this step, right? What does this really mean, right? So this means if you're starting from some point xm and you compute x and z, right? Here the only changing part is xm, right? So yeah. So the only changing part is, so let's say if this is y, right? So we just sum up with all possible y.
Okay.
So how to say that? Yeah, that's a good question, right? Why you write this as a summation? Um, So this is okay. Let me write some. Yeah, next time I should be slower, but you are slow. I cannot finish. But this function, right? You can think this is a function of xm, right? So this function of xm.
Does this mean we're starting at xm?
No. So this is a function of xm. You can basically write this as f x, right? Then you integrate you're starting from x, right? Starting from x, and you want to integrate with all possible value of xm. Right?
What does pxm xn equals to z mean?
Hold on. Let me using let me using the iPad so I can really write. Okay. Let me stop sharing and using iPad. Sharing. Okay. So okay. So here. So here ym is the only change part. So this you can think this as f xm.
What does x, if xm is in the subindex, what does it mean? Does it mean we're starting at xm?
Yeah, we are starting at xm. Yeah.
And xm is random. Okay.
Yeah, xm is random.
Okay, but what's the relationship? Is m smaller than n?
So here m and so that's why I said, right. So for this part,
Yeah.
for this part, for this for this part, right. So m and n has nothing, has no relation at all, right?
Okay.
So so this is just so it's gm. It's just a function of xm, right? So yeah, so this is kind of so p is a px, not px, right? We should use y, right? So this part is just a py xn equals to z, right? This is a number, right? This is a number. It's a function, right? So then we just take x equals to xn.
Oh, okay.
Yeah, so that's why I just said, right, this is a function of gm. So this is what you write is you're starting from x and you want to code this, right?
Yes.
Yeah, so this case, right, can be integral, but so the sum up, let's say is countable, right? So we just sum up all possible gx, gy, right, gy, and the probability of xm equals to y, right? So it's just the integral way to write the expectation. But so for xm equals to y, we really starting from x, right? So that's why we write this. Yeah. Okay. Yeah.
No, I'm still confused. But the thing you write on the right, expectation of x starting at x, gxm.
Yeah.
Does this mean we're what does the x in the subindex mean? It means we're starting at x, so it means the
Yes, from
expectation
x.
is over,
We are starting from x. Yeah.
and the expectation is over xm.
Yeah, the expectation is over xm. Yeah.
Okay.
So what does ex means, right? So ex actually, so x is let's say you're starting from x. X is actually this. Is actually Dirac x, right? You're starting from x, right? Is this. And so this is a mirror, right? So it's a specific mu e mu, right? So you basically ignore this, right? If you are clear but this indicates, right, initial distribution is mu, right? Or the initial distribution is delta x.
Oh, okay.
Yeah. Yeah, I think I'm maybe too fast. Next time I should just write. Yeah, maybe I didn't cover a lot, but yeah, maybe I just go one, just go one step. Okay, just. Uh,
Oh,
yeah, so here, right, let me just repeat, right? So here, so actually xn, right, xn and xm has no relation, right? So if you write like this way, right, it means, right, so ex, right, so here this probability and this probability are different, right? They are basically different. So but so in this part, the only changing part is xm. So this xm is the m state, right, starting from x, right? So for this part is you're starting from xm, right? So you treat xm as a constant, right? You're starting from xm, and you want to compute the probability xn equals to z, right? So that's why I say this part, right, the inner part is just a function of xm, right? So from this step to this step is just expanding the expectation. Yeah, just expanding the expectation, right? So then we sum up all possible choices of xm, right? All possible choices of xm, right? So then just the function, right? Gy, right? This is the probability of gy, right? This is just a definition. Okay. Okay.
okay.
Yeah, you can think for a while. Definitely. So it's just a bit too much information. So you just go through once, you will understand. So,
Okay. I think this is a little bit too fast.
yeah, too fast, right? Because I cannot see anyone right response. So
last
I should
class is
write.
last class is fine, but this class is completely new material.
Oh, yeah. So it's too fast, right? So if I do this fast, maybe people cannot follow, right?
The Markov for me, the Markov the Markov matrix and everything is that's easy, like the finite case or the examples are fine, but then when you moved to the abstract part, it becomes hard to follow.
Maybe from here
Yes.
is
Yeah.
hard, right? From here, right?
Yes, exactly. Yeah.
Yeah, you're right. Yeah. Yeah, it's always hard. So that's why if you see some most people don't talk about this. Okay.
Yes.
So maybe they just use that. Yeah, they just use this property. So maybe it's better just starting from the theory, like from this one. Maybe it's better from starting from this one, and also this, and to do some application. Maybe that's easier, right?
Oh,
Yeah, yeah. I'm very sure, right? People just look at this, it's very confusing, right?
yes.
Yeah. Okay.
Yes.
So as I told you, right? So here, right? So here is, so the only change part is xm, right? It's an expectation. You take an expectation starting from xm. So xm is fixed, right? So it's changing, but it's changing later, right? So that's why I said, right? So you first take a this is a function, right, with initial state x, right? Then you evaluate this function and xm, right?
So the left-hand side and right-hand side are both random variables.
Yeah, these are both random variable, but those random variable is like, so first, this is a function of initial state, right? So this is a function of initial state X. Then you just plug in the initial state as XM. So you get a random variable. This random variable is changing with respect to the initial state XM.
Oh, I see.
So, but this part is different, right? This part is, okay, so you're starting from the distribution mu, right? So this mu is on the whole state, right? This is, and you do the conditional expectation. This is on the whole set. So it's not a, so what does this really means, right? So let me maybe write, right? So let's say if you take omega here, right? Omega is omega 0, omega 1, etc., right? So what is this part? This part actually is, right, if you do the theta m, so what you get, so actually is omega m plus 1, etc. So y compose theta m. So now actually equal to omega m plus 1, etc., right? Okay, so what does this mean, right? So if you condition, right, there's a, so for this path, right, there's a measure mu. There's a measure mu. And if you do the conditional probability, conditional expectation with respect to Fm, right, with respect to Fm. So then basically what this formula says, right? You take the expectation with Fm. And this tells you, right, you just get a new function, which just only depends, which just depends on xm. It just depends on xm. Yeah. It's okay. Yeah.
Okay. I understand the corollary now about the Chapman.
Yeah, Chapman, that's easy, but this
yes.
Yeah, this is hard. I still feel confused. Yeah, for me, I still feel this confused because yeah, I always want to make it like easy to explain, right? But this seems not that easy to explain, right? Yeah. Yeah. So you can think in another way, right? So this mu is on the whole trajectory, right? And this xm, of course, this xm also depends on mu, but this is kind of you restart and xm, right? You restart and xm. Yeah. Yeah, maybe talk more next time. Okay.
Are you going to, can you explain more about the previous part, like which one about the consistency and then the Duncan's pi lambda theorem? Like okay. Does consistency mean that take the whole set and the probability is 1?
The consistency means the.
Do you think we can stop the recording? Or I don't know.
Yeah, maybe I stop recording. Yeah.